Dear students, welcome to the chapter Chiral Drugs. Let us start this chapter by discussing the definition of chiral drugs. Now, the drugs which have chiral centers can be considered as chiral drugs. Here I have given two examples of chiral drugs. Number one is Ibuprofen, that is non-steroidal anti-inflammatory drugs, popularly known as painkiller. That compound has one chiral center. That chiral center is carbon which is attached with the four different groups. One is methyl, one is carboxylic acid, another one is the substituted benzene ring, and the hydrogen is also there, not seen here. The next example is Omeprazole, that is anti-ulcer drug or proton pump inhibitor. This is also an example of chiral drug, but the difference is here we do not have the chiral carbon. In place of that, omeprazole contains chiral sulfur. That sulfur contains four different groups. Number one is oxygen, number two is CH2, number three is carbon of benzimidazole ring, and the fourth one is lone pair. Now next is these chiral molecules have enantiomers. Any chiral molecule will be having pair of enantiomers. Now these pair of enantiomers, when they react with the achiral reagents, achiral environment, then there is no difference in the behavior of these two enantiomers of any chiral compound. But when these chiral compounds interact with chiral reagents or chiral solvents or catalyst, means when they are present in the chiral environment, then these enantiomers behave in a different way. So that is the basis of why chiral drugs, the pair of enantiomers of chiral drugs behave in a different way inside our body, because inside our body we have chiral targets. So these chiral targets are protein, nucleic acids, lipids and carbohydrates. So as because they are all chiral, so chiral drugs behave in a different way. Now this can be explained by using 3-point contact model. The difference in the behavior can be explained by considering Ogston's 3-point contact model. Now if you see this pictorial representation, that this is the target is present inside our body. It can be protein, it can be carbohydrate, it can be nucleic acid, and we are considering that there are 3 points. At these 3 points the drug molecule can interact. Now these drug molecules are the pair of enantiomers. This is the chiral center which is linked with the 4 different groups A, B, C and D. Now in this picture, A is interacting with A prime, B is interacting with B prime, C is interacting with C prime. Now these drug molecule ki enantiomer, that is A and B in this picture, A, B, C, D, they are all in the clockwise manner, but in this picture A and B, they have exchanged their places, so the relationship between these two molecules are they are pair of enantiomers. The C and D are as it is, but A and B are in a different position. So now this chiral molecule, which is the enantiomer of this molecule, when this is interacting with the same target, then only C can interact efficiently with the C prime, whereas A cannot interact with A prime and the B also cannot interact with the B prime. So this is an example of the good fit and this is the example of the bad fit. Means here we will be having more effective interaction, here we will be having less effective interaction. Now these interactions are, the examples of these interactions are hydrogen bonding, ionic interactions, dipolar interactions, ion dipole interactions, pi-pi stacking, hydrophobic interactions. These are the main important interactions between drug and the target when they undergo non-covalent interactions. Other than this, covalent interactions are also possible. Now if we consider this molecule, this is ibuprofen, non-steroidal anti-inflammatory drug. This is the chiral center, chiral carbon atom. Now this center ki absolute configuration is S. How? Carboxylic acid is the first priority, phenyl group is the second priority, methyl group is the third priority, hydrogen is the fourth priority. Now hydrogen is above the plane, so therefore 1, 2, 2, 2, 3 it is clockwise. So in place of R it will be S because the fourth priority group is above the plane. Now this molecule, when it interacts with its target, then there will be three interactions. Benzene ring undergoes the pi-pi stacking, carboxylic acid undergoes the hydrogen bonding, and methyl group undergoes the hydrophobic interaction with its target. And these interactions are more effective in case of the S absolute configuration rather than the R absolute configuration. Means R ibuprofen undergoes less interaction with its target. Now the target in case of the ibuprofen is the one enzyme. Ibuprofen is an example of enzyme inhibitor. The name of that enzyme is the cyclooxygenase. So cyclooxygenase is the target for ibuprofen, where S-ibuprofen has more effective interaction than R-ibuprofen. Now for the chiral drug, when one enantiomer is more active than its another enantiomer, then these two enantiomers can be called as eutomer and distomer. Now let us see what is the definition of eutomer and distomer. Eutomer is the enantiomer which will be having better activity, which is more potent. That is called as the eutomer. Now naturally distomer will be having the reverse type. Means distomer is the enantiomer of the chiral compound which shows the less activity, otherwise the other activity. It may also show the toxicity. Now in the above example of ibuprofen, which is a non-steroidal anti-inflammatory drug, S-ibuprofen is an example of the eutomer and the R-ibuprofen is an example of distomer. Means S enantiomer will be having good fit and the R enantiomer will be having a bad fit with its target. The target is cyclooxygenase. Now another example of the chiral drug is omeprazole. Now omeprazole also will be having two enantiomers. One is the S-omeprazole, another one is the R-omeprazole. S-omeprazole is more active, therefore S-omeprazole will be considered as eutomer. The R-omeprazole is less active, so therefore R-omeprazole is an example of distomer. Now this is the example of S-enantiomer of omeprazole. This is the example of the R-enantiomer of omeprazole. So let us see how it is. This sulfur is chiral, as already we have discussed. Now how this absolute configuration of this center is S. Now let us put the priority. Oxygen is the first priority. Benzimidazole ring is the second priority. This CH2 is the third priority. Lone pair is the fourth priority, which is pointing back. So therefore 1, 2, 2, 2, 3 anti-clockwise. Fourth priority group is at the back. So therefore this chiral center has the S absolute configuration. Now in this case, keeping constant the two means oxygen and the benzimidazole ring ki orientation. Lone pair and the CH2 group, they have exchanged their orientation, so therefore it will be having the opposite absolute configuration, that is R. We can try 1, 2, 3 priority also. Let's see. Oxygen is the first priority, benzimidazole ring is the second priority, CH2 is the third priority, and the lone pair is the fourth priority. So 1, 2, 2, 2, 3, this is anti-clockwise, but the fourth priority group is above the plane, so therefore this anti-clockwise orientation will give rise to our absolute configuration. Now the third example is the salbutamol, very popular medicine for asthma patients. Now salbutamol is also an example of chiral drug, where this is the structure of the salbutamol and this is the chiral carbon which makes salbutamol chiral. Now the absolute configuration of this center is, let us see, oxygen is the first priority, aromatic ring is the second priority, this CH2 is the third priority, and the hydrogen is the fourth priority, which is not seen and will be considered as a reference. So 1, 2, 2, 2, 3 anti-clockwise. Now 1, 2, 2, 2, 3, 1, 2, 2, 2, 3, this is clockwise because this is oxygen is the first priority, carbon attached with the nitrogen is the second priority, and this is the third priority. So 1, 2, 2, 2, 3 clockwise. The hydrogen is below the plane, so the absolute configuration of this salbutamol is R, and therefore this is absolute. Oxygen is the first priority, carbon attached with the nitrogen is the second priority, aromatic ring is the third priority, hydrogen is above the plane, so 1, 2, 2, 2, 3 it is clockwise, but hydrogen is above the plane, so this will be considered as the S. So this is distomer, this is less effective, this is more effective as bronchodilator because this is used for the treatment of asthma patients. Now let us go to one ratio. That ratio is known as the Eudysmic ratio. Now what is the definition of Eudysmic ratio? Now this Eudysmic ratio is the ratio of the potency of eutomer divided by potency of distomer. Means potency of the more active chiral drug divided by potency of the less active chiral drug. And it represents, so what is the significance of this Eudysmic ratio? Eudysmic ratio represents the difference in the pharmacological activity between the two enantiomers. Now more this ratio will be, it indicates if this ratio is more, what does it mean? If this ratio is less, what does it mean? Let us take few examples. Like Eudysmic ratio of S and R propanolol is 100. Propanolol is used for the treatment of the high BP. This is an example of what? Antihypertensive drug. So this ratio is 100. Now take another example, that is Eudysmic ratio of this molecule dextritimide. Here also we have the chiral center. So here the Eudysmic ratio, S enantiomer is the eutomer and the R enantiomer is distomer. This is used for the treatment of the Parkinson's disease, and this Eudysmic ratio is 10,000. So first we have discussed the definition of chiral drugs, examples. Next we have discussed 3-point contact model. Next we have discussed what do we mean by the eutomer, distomer with examples. Next we have discussed Eudysmic ratio. Now the sixth one, that is Pfeffer's rule. Now this rule states that higher the Eudysmic ratio, higher will be the activity of the eutomer. Let us see this example. Let us compare this. Now this is, take the two drugs, both are antihypertensive. One is atenolol, another one is metoprolol. Now when we take atenolol, metoprolol, both are chiral drugs. In both the cases, S enantiomer is eutomer, R enantiomer is distomer. Now when we consider Eudysmic ratio of atenolol, then that ratio is 40. Whereas when we consider metoprolol, then Eudysmic ratio is 200. Now this indicates that S-metoprolol is more powerful antihypertensive agent than S-atenolol. This can be decided by referring Eudysmic ratio. And this is called as the Pfeffer's rule. Now let us consider the role of chirality in biological activity. Now which one is more active? That is called as the eutomer. The chiral drug which is more active, that will be considered as eutomer. So that will be used as medicine according to FDA. Now what about the distomer? Now distomer will be having varieties of properties. So what properties distomer can exhibit? Let us discuss one after another. Now the case number 1, distomer may have no activity. It does not have, it may not show any activity. Case number 2, it may have the same activity, means the distomer also will be active against same disease. Case number 3, that is, it is active but it is activity is less. Next one is distomer will be having a completely separate profile. It will be showing good activity against some other disease. And the last but not the least, it may be having toxicity. So eutomer will be more active, but there is no guarantee about the property of the distomer inside our body. It can be different types. So let us take some few examples how distomers show different properties. Now case example number 1, A category, means with no side effect, like propanolol, atenolol, metoprolol, this LOL series, which are important drugs for hypertension. In all these cases, distomer is R. So this R does not have any side effect. The second example under this category is Omeprazole. In Omeprazole, which is anti-ulcer drug, here also R will be distomer, which does not have any side effect. Salbutamol, that is a bronchodilator, is used for the asthma patients. For this molecule, S is the distomer and they do not have any side effect. only they are simple distomers. Now let us go to the B category, where the distomer will be having toxicity, and in this case the most notorious example is the example of thalidomide. Now this thalidomide, the structure is this, and this is the chiral carbon attached with the nitrogen thalimide ring. This, in this case, this is the S absolute configuration, this is the R absolute configuration. Now this compound is actually Eutomer and was treated was given for the pregnant ladies as sedative drug. But when it was given as sedative drug at that time, we were not aware of this problem, that enantiomer of a chiral drug can show different properties. So when it was given as a racemic mixture. So inside those ladies body, that eutomer did its work, but this distomer showed toxicity on the baby, so not on the mother. So this is called as teratogenic. So teratogenic means that bad effect, means toxicity will be shown on the baby inside mother's body, not on mother. So the medical term of that is teratogenicity. So thalidomide S enantiomer was teratogenic, whereas the R enantiomer was sedative drug. Now under this category, the second example is the DOPA. We know that L-DOPA is used as anti-Parkinson's drug, but the D-DOPA is toxic and it leads to agranulocytosis. Now this is yet another example where the one enantiomer is definitely eutomer, but the distomer is having toxic effect. So that is tetramizole. So tetramizole is a nematocide. Nematocide means which kills nematodes, means a type of microorganism, where the eutomer is a L enantiomer, and the D enantiomer has the various side effects like headache, vomiting, stomachache, like this. No, so A category is the distomer does not have any side effect. B category is the distomer has toxicity. Now the C category, we will switch over to the C category, where the both enantiomers have the different medicinal importance, means therapeutic value. And the most popular example under this category is the Darvon and its mirror image Novrad. So the Darvon is, this is the chiral, there are two chiral centers are there. Now these two are the pair of enantiomers. Now the Darvon is painkiller and the Novrad is antitussive, means anti-cough. So this is OCOET. Now with this we have completed third category also. Now we will go to the D category, where we will discuss one example where the combination of the chiral drugs will give the better effect, and that is called as the synergistic effect. Now then, an effect produced by the combination of minimum two or more substances than produced by some of their individual effects. That effect is called as the synergistic effect. When means, what is the meaning of that? The simple meaning of this effect is the when we will combine these two drugs or more than two drugs, it will be having better effect than the individual. So the example is this example where the molecule is cycletanin. This is antihypertensive, means BP lowering agent. So in this molecule, when it is used as a racemic mixture, then that effect will be better than the R enantiomer. Now another example of this type of example of the synergistic effect is the dobutamine. Now dobutamine is used for the heart failure, cardiac patients. For the treatment of the cardiac patients, dobutamine is used. And the dobutamine is used as a racemic mixture. Now because of the different mode of actions of plus dobutamine and the minus dobutamine, the combination will be having better effect on the cardiac patient. Now we will go to the E category. Before that, let us revise the four categories. A category, distomer does not have any side effect. B category, distomer will be having toxicity. C category, distomer will be having activity against another disease. Both are good, but for different diseases. Number 4 is synergistic effect. Sometimes racemic mixture will be having better effect. And the last one, that is metabolic chiral inversion. Now in this case, the best example of metabolic chiral inversion is the ibuprofen. Now this is inside our body. Our ibuprofen, which is the distomer, gets converted into the S-ibuprofen by taking the help of the enzymes. So if we take the racemic mixture of ibuprofen, then distomer inside our body will be converted into eutomer. So let us see how the distomer, which is R ibuprofen, gets converted into eutomer S ibuprofen. Now this R ibuprofen has this functional group. This functional group will be converted into its ester by using acyl coenzyme A synthetase. Now it will be converted into, see here, inversion has happened. That is ibuprofen coenzyme racemase. So this step, inversion, this is R and it is getting converted into S. Now the third step and the last step, that is hydrolase, means this hydrolysis will happen and it will be converted into the carboxylic acid. So in this way, by taking the help of the different enzymes, R ibuprofen gets converted into S ibuprofen. So this is a very good example of metabolic chiral inversion. Another example is that thalidomide, that is R enantiomer, which is, but here it is happening in the reverse direction, means eutomer gets converted into distomer. In case of ibuprofen, it is happening in the good direction, means distomer was converted into eutomer. But when it comes to thalidomide, then eutomer gets converted into distomer by taking the help of different enzymes in liver. So these are the two examples of metabolic chiral inversion. Now let us go to the synthesis of ibuprofen and its pharmacological activity, means mode of action. Now we are starting from isobutyl benzene. Now isobutyl benzene, when it is treated with HF in presence of acetic anhydride, acetylation is happening. The acetylation is happening at the para position because of the steric crowding of this isobutyl group. This group is ortho-para orienting, but ortho position ki acetyl group is not going, or it is going very less because of the steric crowding. Now in the next step, a compound is getting reduced, and in this compound the reducible group is C double bond O, means ketone. Ketone gets converted into the secondary alcohol, and in this step we are getting this chiral center because this carbon is attached with the 4 different groups. One is the OH, another one is the aromatic ring, another one is methyl group, last one is the hydrogen. Now because we are not using any technique of asymmetric synthesis, this compound we will get as a racemic mixture. Now this compound, when it is subjected to the carbonylation, means insertion of CO. So if you insert this CO in this bond by taking the help of transition metal palladium, this secondary alcohol gets converted into the carboxylic acid by carbonylation. Now after this compound is racemic mixture is subjected to the resolution by taking the help of this carboxylic acid. This is the racemic mixture of carboxylic acid. Now this carboxylic acid, by using how to do the resolution of racemic mixture of carboxylic acid, by using optically pure base. These bases are alkaloids. So by using this alkaloid, we can separate this R ibuprofen and the S ibuprofen. Now next isosynthesis is over. Now actually this separation is not required because of the metabolic chiral inversion. In racemic mixture if we take, then inside our body distomer R ibuprofen gets converted into the S ibuprofen. Okay, fine. Now let us see what is the mode of action of ibuprofen. Now inside our body, arachidonic acid gets converted into prostaglandins in various steps, and in one step the catalyst is cyclooxygenase. I repeat, inside our body arachidonic acid gets converted into prostaglandins. It is an example of multi-step synthesis, and in these several steps, in one of the steps the catalyst is cyclooxygenase. Now what is the role of prostaglandins? Now prostaglandins will be having good role and bad role. Means what are the good roles? It prostaglandins are used for the protection of kidney and mucosa. At the same time, in the site of inflammation, prostaglandins are responsible for pain. So it is having two roles inside our body. It has some good role, it has some bad role also. But if we want to control inflammation, then we have to take, doctors give non-steroidal anti-inflammatory drugs, as for example ibuprofen. Now this ibuprofen interacts with the active site of cyclooxygenase so that arachidonic acid does not get converted into prostaglandin. So in this way, ibuprofen blocks or inhibits enzyme cyclooxygenase. So pain does not happen, inflammation gets reduced. Now see, this is the pictorial representation of mode of action of ibuprofen. Now this is the cyclooxygenase symbol and this is the active site. In normal case, here arachidonic acid comes and it gets converted into prostaglandins in multi steps. Now when ibuprofen comes, then ibuprofen interacts with the cyclooxygenase, and how it interacts already we know. With the carboxylic acid it undergoes the hydrogen bonding, with the benzene ring it undergoes the pi-pi interaction, and with the methyl present in the chiral center undergoes hydrophobic interaction. So these are the 3-point contact model. Now if ibuprofen interacts with cyclooxygenase, then prostaglandin synthesis gets disturbed. So inflammation, slowly it goes. Now this is the active site where the carboxylic acid undergoes hydrogen bonding. This methyl group in the chiral center undergoes hydrophobic interaction with the active site, and this benzene ring will undergo the pi-pi stacking with cyclooxygenase active site. So with this we have completed ibuprofen synthesis and its mode of action. It is an example of enzyme inhibitor and is used to treat inflammation. Now let us go to the second molecule, that is metoprolol. So metoprolol is used to decrease blood pressure for those patients who have cardiac problems. Means heart patients, if they have high BP, then to treat that condition doctors usually give metoprolol. Now metoprolol is an example of chiral drug and the S enantiomer is Eutomer. Now its mode of action is, it is beta blocker, beta adrenergic receptor antagonist. Now first, as usual, we will synthesize this molecule and then we will see its mode of action. Now it is a para disubstituted phenol, means phenol ki para position we have CH2COOMe. Now when this compound is treated with the anhydrous potassium carbonate, which is base, anion gets generated O-. Acetone is a solvent and this is benzyl bromide is acting as alkylating agent, means that phenolic OH undergoes O alkylation under this condition. So this compound gets converted into this molecule. AR is the aromatic ring, O is that this O, and then in place of this hydrogen we have benzyl group coming from benzyl bromide. Now in this molecule we have reducible group is the COOMe. When this molecule is treated with lithium aluminium hydride, then ester gets converted into primary alcohol. So this part gets converted into CH2OH. So overall at the para position of OCH2PH, we will, means BN is the abbreviation of the benzyl group, its para position ki this CH2 is common here, and this COOMe ester group gets converted into CH2OH. Now when it is treated with the sodium hydride is a base and it takes up the hydrogen from alcoholic OH. Now the CH3I is methylating agent, so OH gets converted into OMe. Now next is the hydrogenolysis. Hydrogenolysis is used to break this bond, benzylic carbon oxygen bond. So this compound is this after two steps. Number one is the O-methylation, number two is the hydrogenolysis. We have benzene ring, para position ki phenolic OH and CH2OMe. Now this compound is reacting with epichlorohydrin. So epichlorohydrin has unstable what it is called the epoxide ring, and this epoxide ring will open up by phenolic OH oxygen. So this oxygen will attack here and this will go here. So you will be getting this oxygen will be connected with this CH2. The next carbon key will be having OH. This carbon also will be attached with the CH2Cl. So this oxygen is the phenolic OH. This is the epoxide key CH2. This is the next carbon which will be having OH, and this is the chiral center. And this is what it is called when it is treated with the RR cobalt silane complex, then we get exclusively this enantiomer. So this enantiomer means which will be useful for the synthesis of Metoprolol. So this is now we will be having another intramolecular SN2 reaction. Means this nucleophile, again this nucleophile will attack here and the epoxide ring will open up. So that is that. What is that nucleophile? Nucleophile is isopropylamine. The isopropylamine is the nucleophile which will attack here. The OH will come into the chiral carbon. So in this way we will be able to prepare Metoprolol with some para substituted phenol. So this part I will repeat once. Now this we have prepared previously. First we have blocked this by benzylation. Then here we had ester at the starting compound. Ester was reduced to primary alcohol by lithium aluminium hydride. Then that alcoholic OH was methylated, and we got this after deprotection we got this compound. This compound will be acting as the nucleophile, and the nucleophilic ring opening of epichlorohydrin will occur. Now later what will happen, resolution will be performed on this compound, and in order to synthesize S enantiomer of metoprolol, this enantiomer we have to consider, other enantiomer will be kept aside after resolution. Now this molecule will undergo the intramolecular, this is nucleophilic attack will take place, SN2 attack will take place, chloride will go, it is a good leaving group, we will get this epoxide ring. Now this epoxide ring again it will open up by the attack of the nucleophile. That nucleophile is isopropylamine. Now this isopropylamine will attack this unsubstituted position and he will end up into this compound, which is the Eutomer, Metoprolol. Now what is its mode of action? Now already we know that it is a beta blocker, and it is used for the treatment of the high BP for the cardiac patients. Okay, so this is that cardiac patient has what it is, angina problem and also tachycardia problem. Angina means they will be having some block in the heart, and so they will be having chest pain, and the tachycardia is heartbeat will be more than normal. Its opposite is bradycardia, means if heartbeat is less than normal, then that situation is called as the bradycardia. Now this is the heart patient might be having angina problem, or it might be having the tachycardia. So in that case, in addition, if they have high BP, then doctor usually gives this medicine, Metoprolol. Now this is a beta blocker, as already we have discussed this. Now how it is the symbolic pictorial representation of how it is a beta blocker. Now this is the beta 1 receptor present in the heart. So this is the binding site. Now in this binding site, actually normally adrenaline comes. This is the neurotransmitter. And when adrenaline comes, then it leads to the vasoconstriction, means the blood vessels diameter decreases, which leads to the increase in the BP. But for the high BP patient, BP should not increase further. So this reaction should not occur in high BP patients having cardiac problems. Now see this picture. Now here also you will be having this beta receptor which is present in the heart, means that is beta 1, but now this binding site is occupied by metoprolol, means S-metoprolol, which is the eutomer. Now if it is occupied by this molecule, adrenaline cannot come and interact with the binding site, so vasoconstriction does not occur. So in place of that, what happens is the vasodilation and the BP goes down. Okay, so let me stop. Thank you.